Hi everyone. The fifth part of the experiment on Introduction to Arduino requires us to write a program and simulate a circuit to control the brightness of an LED using a push button such that the brightness reaches from minimum to maximum in 5 pushes. That means I should push the push button 5 times, and each time the intensity should increase uniformly, and in 5 pushes it should reach from the minimum to the maximum. The intensity should again go back to 0 when I push the button for the 6th time. That means, say if I was representing the brightness and connecting the LED to a certain pin where I'll be using analog write function to write the intensity. So I know that this intensity would then have to be on a scale of 0 to 255, right? So what the question says is that the circuit should be such that the intensity scale from minimum to maximum, which is fed into this LED, should be such that it should be increased such that every time a trigger comes in the form of pressing a push button, it should increase the intensity by some interval, 2, 3, 4, and 5. So eventually in 5 steps, it should reach from minimum to maximum. So this tells us that if this has to happen in 5 steps, each of these steps should be of level 51, like each of these increments should be of 51. And it also needs us that the moment I press it the 6th time, intensity should again go back to 0. Now, if we look at the circuit and how it has been wired, we understand that there are 2 main components here. One is the LED, and the second one is the push button, which should act as a trigger, right? So we have 2 independent circuits, as you can see here. We've got an LED connected through a resistor connected to pin number 11. That means, say this is coming from pin number 11. So we've got a resistance and an LED. Right? And we also have an independent circuit, a separate circuit, connecting the push button with pin number 8. So before that, we noticed that the push button has one terminal connected to 5 volt and the other side connected via a resistor to the ground. Right? So it's a circuit like this. So we've got 5 volt here. This is connected to the ground. There's another resistor connected to the ground. And this is where the push button is. So when I press this, when this button is pressed, these 2 terminals actually get connected to each other. Right now they are in open circuit, and we'll see this just in a while, how they are open circuit, how to check this. So these 2 are connected internally. These 2 are connected internally already, but these 2, this terminal and this terminal, will be connected only when this button is pushed, right? So this is what that state is showing. So right now the button is not pushed, so the circuit is not complete, right? You notice what is happening here? The output across this resistor with respect to ground is actually being sent all the way to pin number 8. That means this is actually going to pin number 8. What this tells us is that whenever the button is pushed, that means it's in a state like this, the circuit will be complete, and that time pin number 8 will get a digital value high, because this whole 5 volt is going to come across this resistor. And if I was just looking at digital values, if I was reading digital values, it would say it's a digital level high. That means when the button is pushed, pin number 8 gets a high, and whenever the button is not pushed, means it's released, the circuit is not complete and you get a low value at pin number 8. Okay. So what we understand from here is that we've got to use whatever is happening at pin number 8, the input, whatever is happening at pin number 8, that has to be used to program and determine the value that should be written to pin number 11, right? That means obviously pin number 8 needs to be an input pin, and pin number 11 here needs to be an output pin, right? And we've also established that since we are going to write a code, that means we can initialize the brightness to be something like 0. And every time you notice that the button is pushed, this brightness should be increased by 51. And you also need a condition that when this reaches 255, right, the moment this exceeds 255, then you again set brightness as 0. So these kind of conditions need to be incorporated in our code. Now it looks pretty simple, but there is some additional aspects that we need to keep in mind when we are dealing with a physical push button. Okay, so just let us quickly see how the connection of a physical push button looks like, and then we'll talk about this phenomenon. So on Tinkercad, I've connected one ohm meter, and a push button, as you can see, has 4 terminals, and this is one button. So you notice terminal 2A and 2B. So what this means is that these are connected internally, like this 2A and 2B is connected internally. Similarly, terminal 1A and 1B are connected internally. It is between 1 and 2 that you notice that there is an open circuit, and this is what gets connected every time you press the button. So just to check that quickly, let us connect an ohm meter, right? And if I start simulation, right now it shows me mega ohm. That means this is an open circuit right now. And if I press this switch, you notice that it shows me 0 ohm. That means it's a short circuit. I again release the switch and it is again open circuit. If instead I had rotated this, I'm measuring resistance across these 2 terminals. We know that this is already connected internally, right? So it should show us a 0 ohm, which is true. That's how a physical push button looks like, the connections. The important aspect that I was talking about when we talk about a mechanical switch like a push button is the concept of debumps. Now, many a times what happens is, and this is not an error, it is just a physical constraint of any physical or mechanical device. And that is that whenever you have a physical connection, a mechanical switch, what's going to happen is the moment you press this, right? And ideally, these should make a contact immediately, and both these brushes should make a contact immediately. But in a physical device, what would happen is oftentimes this contact may be made, then for like a fraction of a second, momentarily, the contact may be broken, then it may be made again, because you are physically pressing this switch, right? So push buttons often generate spurious or like these open or closed transitions when they are pressed. And this is simply because of a mechanical or physical constraint, right? So these transitions, they may be read as multiple presses, like as if the microcontroller thinks that the button has been pressed multiple times, but it's actually not been pressed multiple times in a very short duration. It was just one press, but it is the physical limitation which has led to this kind of a confusion. So these buttons are very bouncy in the sense that if you press a button, it may not immediately make a complete connection. In fact, it may have made a connection on one side, but the second side was just a fraction of a second late. And this making and breaking of contact is called bouncing, right? And it is not a defect of the button. It is just a limitation of this physical mechanism, this mechanical mechanism, right? And this kind of a bouncing happens within milliseconds or microseconds, right? But your microcontroller is processing everything very fast, and it may consider as if these were 2 different states of the buttons between one single transition that you wanted to make. Because of these multiple transitions, multiple presses in a very short duration, your microcontroller will think that these are 2 different states of the buttons. So it is important that whenever we are pressing a button, we consider some sort of buffer time. And after that short buffer time, we again note the value. If it is still on, we consider that yes, this is on, right? So you pressed a button and you consider some buffer delay of say 5 seconds. And after 5 seconds, the button is still closed. So you say, yes, the button is closed. So this kind of a debounce mechanism needs to be brought in whenever we are dealing with a physical switch. And this will have to be a part of our code. Okay, so let's move on to the code. Pin number 8 is input, pin number 9 is output, pin number 8 is what is going to be connected to the switch, and pin number 11 is what goes to the LED. So this is how the code would look like. Let us start with initializing that LED level is 0, the brightness is 0, switch pin is 8, LED pin is 11. We are also defining a few Boolean variables here to show what is the last state and what is the current state of the button. So remember, when should the LED brightness be increased by an amount 51? So if you were just looking at the state of the button and we said, let there be a last state, like the last state of the button, the previous state, and let there be a current state of the button. And there should be some action, right, based on this. So if the last state is low, that means the button was actually not pressed, right? So button is not pressed means the last state is low, and now the new condition is that it is pressed, it's high. In such a case, brightness should be increased by an amount 51. For all other cases, if the previous case was low and the current state is also low, no action, right? Means you did not touch the button. If the previous case was high and even right now it's high, that means you press the button and you are still holding it down. Still nothing should happen, right? So no action. So this is the case. This is the condition that we are looking at. So if you look at the code, essentially that is what is happening. And we'll talk about what is this part in just a little bit, but let us look at the other aspects right now. So to start with, we are initializing both the previous state of the button and the current state of the button as Boolean variables low, right? In setup, we will initialize what our pins are supposed to be. So switch pin, which is pin number 8, is designated as input, and this is pin number 11. This is designated as output, as discussed earlier. We'll come to this in just a second. If you look at the loop, which is the main part of your code, you notice what are the conditions? This is some function which we have written above, which I'll come to. So what is the condition? It says that if the last condition of the button was low and the current condition of the button is high, these are all both Boolean variables. In such a case, LED level is incremented by 51, and you notice that at this point what you should also do here is that once you have checked this, let the current state become the previous state for the next turn onwards. So the current state of the button now, after this whole cycle has been completed, that becomes the last state for the next cycle, right? So this should now become the last state for the next cycle to run, right? And this should continue. And what should now finally happen? If LED level exceeds 255, you again switch it back to 0. This will happen only if LED level is 255. Otherwise, whatever is the LED level, just write its value, analog write its value to pin number 11. Right? That is the LED pin. Make sense? Now let us look at what is happening in this part. This is one function called debounce that we have defined specifically to avoid that condition of debouncing. Right? So what this says is, it's just a function definition. So it's saying, let there be a function called debounce, right? That takes an argument, and that argument is also a Boolean variable, and that argument is last. Okay? Means this is a last state. So the debounce function would take the last state as the input and return something, and return the current state, right? So how should it determine the current state? Current state is equal to the digital read value on switch pin. So for example, I have a variable current, it is doing digital read on switch pin, that is pin number 8, right? So suppose I've pressed the switch, and right now my switch pin, that is pin number 8, is reading what? It's reading a high, right? So that means current is now high. Okay. If last is not equal to current, meaning whatever is the input that I have given last, if that is not same as current, then delay, wait for 5 milliseconds, right? And then again read the value in switch pin. Means wait for 5 seconds. If they are not the same, if last was low and current is high, means it's not the same, just wait for 5 milliseconds and again take the reading at pin number 8, and then whatever is the value after 5 milliseconds, just return that value. Okay. So what this function is essentially doing is just taking a buffer time of 5 milliseconds and just ensuring that the value that you get at any given instant, that value is the same value, like whether the switch is on or whether the switch is not pressed, that value remains the same even after 5 milliseconds. This is done simply to debounce the possibility that there are some spurious, erroneous transitions when a mechanical switch is being pressed. Right? Because that is what we are using here, if you notice. Right? So it says current button be debounce last button. So you remember what we had initialized last button as low. Right? So it says debounce low. This is what the variable last is to start with, right? And now I have pressed the switch. That means current is now high, which means this loop is now true because last is not equal to current. So what we'll do is just wait for 5 milliseconds, again read what is there in pin number 8 and just return that value. If it's high, fine, it's high. Okay, so that is what gets saved in current button. And that is what is then in the next step checked whether it's high, and if the previous case was low, then you increment the intensity. What happens is if this is not true, if this is not true, then this part of the loop does not run, right? And you just simply return whatever is the current value. That is simply what is the value at switch pin. If they are same, great. There's no need to wait. Just take that value. So I'm back in Tinkercad and I'm selecting a breadboard and the Arduino Uno board. I need a push button and a resistor. So let's let this lie here somewhere. I also need an LED, which I'm going to place here, and I'll use this resistor. This is the P side of the resistor. So from the P side, I need a connection to pin number 11, right? Make sure you follow the grids and then readjust the wires so that your overall circuit looks neat. So I'm just choosing blue color for this wire. I need the N side of the LED to be connected to the ground. So let me just make a quick connection between this rail and the ground. Okay. For reference, I'm taking the color as black. All right. Now this circuit is complete. The next step I need to do is make this independent circuit of push button, where we need one side of the push button to be connected to plus 5 volts. So let me take this and let it go all the way to plus 5 volt. Let's take this as red. And the other side needs one resistor, which I've connected directly to the ground, right? And now across this resistor, I need one signal to go to pin number 8. So I'm going to take another color, say purple. So it looks like my circuit is complete, and I'll now go to the code, go to text, and write my code over here and just start simulation. Okay, so this is going to work when I press the button. So right now the LED is off, and now I press the button once, the brightness has increased. Another time, brightness has increased a little bit. Third, fourth, and fifth, 5 presses, it has reached maximum. The 6th time, it again goes back to 0. Right? Let's zoom in and view it once. So 1, 2, 3, 4, 5, and goes back to 0 in the 6th time. So this is how I can control the brightness of an LED using a push button. Thank you.